and today I'm going to go do this one problem from that nationals round. That one problem being I'm given a value of q, and I know that p to the power of q minus 1, if that's a multiple of 1001, then the number of possible values of p that are positive and less than or equal to 1000 is 80. And I need to find out the number of possible values of q that are positive and less than or equal to 1000, and all that I said previously holds. So right from the start, I know that I can do 1001, that's going to be 7 times 11 times 13 from those prime factorizations, and I can split them up with some mods thanks to Chinese remainder theorem. E to the power of q is congruent to 1 mod 7, and p to the power of q is congruent to 1 mod 11, and p to the power of q is congruent to 1 mod 13. I can even say, thanks to Fermat's little theorem, that p to the power of 6 is congruent to 1 mod 7 and the like. And I already know that for a set value of q, I can manually calculate the number of possible values of p by doing some mod work and then considering like congruences up to 1000. So the problem is there's 1000 or so values of q that I need to check. And this is a sprint problem. I don't have that much time. I'm going to need a lot more efficient strategy than that. And in order to do this, I need to go take out my group theory things. So here's the thing. So a long time ago, there's this guy named Gauss who did some math work and some remainders, as well as a mathematical concept called groups, where basically there's some operations where if you do anything to the operation, it will stay in that set. There's inverses, and there's an identity element, and associativity holds, all those things. And now Gauss decided to take a look at, let's say, a prime number r, and then all the positive integers that are less than r, so 1, 2, all the way up to r minus 1. And then how about considering multiplying any of those two values and then taking the remainder? I mean, none of them is going to be a multiple of r, so of course in the end this will end up being a group. But not just any group, a cyclic group. Basically, Gauss showed that there is going to be some value a where for a given prime r, such that that order of a is equal to r minus 1. What this basically means is that a to the power of r minus 1, I'm going to go write that down. So there's going to be a, where a to the power of r minus 1 is going to be congruent to 1 mod r. And not just that, if you do any positive value that's less than r minus 1, you're not going to get that. Basically, a is a generator of that cyclic group, and Gauss showed that this is a thing for every single prime number r. And now we can also say that because of that, a to the power of something, where that something, as it goes all the way up, it will result in every single different value. That's generating a cyclic group. So what does this mean? Let's think. So I'm going to go consider something along the lines of, say, a to the power of q, or something like that. Well, when will that result, if you raise that to the power, when will that result in the remainder being 1 mod r? Well, let's raise it to the power of r minus 1, of course, since you can then apply those exponent things, but then maybe it could happen earlier. So let's divide that out by the GCD of q and r minus 1, because then the q and the GCD of q and r minus 1, that would like divide out and then result in like a whole number times r minus 1, and that would still result in 1 mod r. And that ends up being the order of a to the power of q. And then from here on out, we can basically say that since raising those like a to the power of q will like generally vary, we can definitely say that there's going to be solutions where as we go from k times r minus 1 over GCD of q and r minus 1, then as like k goes up, it will like result in like another solution or so, all the way up to, once it goes up into like GCD of q times r minus 1, then I think it will start to like repeat and stuff. That's all the cyclic group things. And fortunately, being able to recall that means I can actually put that to good use. Going back to all those 7, 11, 13 primes right over there, I can now actually start to go apply that. So let's see. So I can say that the GCD of q and 6 times the GCD of q and 10 times the GCD of q and 12 is going to be 80. Now I'm going to need to think of some possible factors that should work. Well, I think the biggest constraint is going to be the GCD of q and 10 because of that 5 thing. Neither of these could have factors of 5. And also, this is a 6, which is highest exponent of 2 is 1, and then 12, highest exponent of 2 is going to be a 2, and then 80 is 16 times 5, highest exponent of 2 is going to be a 4. So this thing must be a 10. And then eventually from there, we can find that this has to be 4, which makes this have to be a 2. And then we can, from here on out, let's piece this all together. So this means that q is equivalent to 20 or 40 mod 60. And from here on out, let's just use all the summation thing with this arithmetic series thing and sum up from all those like 60 blocks from like 0 all the way up to 960 and then add a few more just to get to that 1,000. When you're all done, you can do this on your own. The answer is going to be 17340. Good thing I went through group theory.
Hi everybody, this is Tim. Hope you're enjoying our videos. If so, you know what to do: like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.